This is lesson 1 of unit 4. Air moves in patterns in Earth's atmosphere. Here we've got a photo of, this is actually really close to us. This is in Point Reyes National Seashore. It's north of San Francisco. This is a road. The parking lot is like down here. If you've never been here, you can see the shore. But this is an example of how the wind affects different things. And so this lesson is about how air moves in patterns and affects things across Earth. And this tree, how it's all slanted like this, right, is an example because this is along the way, this road up back this way goes to the lighthouse at this park, and it's always really windy going in this direction, so it has forced all these trees along this path to grow in like a curve. It's pretty neat. Okay, so this first thing. How is it possible from dust from the Sahara to end up in the Amazon? So scientists have been able to track through satellites and through other means that a lot of one of the main reasons why the Amazon rainforest is so lush is because sand and nutrients from dust storms over in Africa blow over the ocean and end up in South America. And so how do they get there? Well, it gets there from wind, right? The sand isn't floating on the ocean, so it's got to be the wind. And here we go. So exploration 1 is about modeling wind and convection. So this is mostly talking about atmosphere, right? And the atmosphere is gas that is the gases that surround the Earth. And so this mentions that, although we can't see the atmosphere or the air is matter, and just like, a liquid, right? If you think of a liquid, how a liquid moves around on things, gas is the same. We just can't see it with our eyes. We can see the effects of it, though. So, you can see effects of it blowing or that type of thing. But you can't actually see the molecules that are making up the wind. And here it's talking about how energy, the energy that drives wind is primarily coming from the sun. So energy from the sun that comes to the Earth can directly heat the atmosphere, but also the sun will give, this talks about, temperature differences. So, there are areas near the equator, right? Well, let me just do a little quick drawing. Like if you are Earth, the sunlight is coming over here, and the Earth is at a tilt, right? Like, so pretend this is the equator, and these are the poles, right? The Earth's at a tilt, but as the Earth spins around, the center portion of Earth is always going to be getting more sunlight than, say, the poles, right? And so it's warmer near the equator, which we know, than it is at the poles. And because there's temperature differences there on the land, it also, heats up the air around it and makes the air move around differently. So there's a lab. We're going to skip this. So this talks about formation of wind. What is actually wind? And so wind is the differences in air pressure. So this says at any given time, there are air temperature differences all around air. As air gets warmer, it expands and its density decreases. Here's an example of a low density. And so high pressure air flows towards low pressure air, causing wind. So in this example, we've got high pressure air over here, we have low pressure air over here, and wind is actually the idea that the wind is would be going in this direction. One way you can think about this is it's the same as hot things going to cold things, right? Hot has more energy, so it goes to cold things with more energy. In this example, you have these two columns of air here, both of the exact same amount of space or volume, but this has more air molecules in it, right? And because it has more air molecules in it, it has more energy. So again, you have this phenomenon of more energy is going towards less energy to balance out. And this is what we feel as air, is basically always the high pressure going to low pressure air. So this talks about convection, and convection can be seen in lava lamps. So convection is the idea of you have warm air, and warm air will be traveling up, right? Because warm air is going to be less dense because the molecules are going to be, spreading apart. And as it goes up, it's going to displace colder air. The colder air is going to go down. And you can see this in a lava lamp, because in a lava lamp, what you don't see in these pictures is there is a light bulb, right? There's a light bulb right here. That's where the light bulb is. And so the light bulb heats up this, there's normally oil, and you can see it with the blobs of color or wax. And what happens is the oil and the wax at the bottom of the lava lamp will heat up. And so what you get is you have all these molecules in the wax, and they're really they're spread out more because they have more energy. So they're moving around more, and they become less dense, which means that they want to float up towards the top of the lava lamp. Now, when the wax gets to the top of the lava lamp, the reason they use oil and wax is because oil doesn't change its density as much as wax. So the wax expands more. So once the wax gets to the top, up here, the oil up here, since there's no light bulb, it's cooler up at the top of the lava lamp than at the bottom. So what happens is the molecules start cooling down and they get closer together, right? They're all much closer together, which makes it more dense, which makes those molecules fall down. And so that's that's convection in action. Which statements about air in the atmosphere are true? Warm air pushes cool air downward. And this would be true. You can kind of use this to see that. Warm air is going up, it's pushing the cool air down. Rising air cools and may become more dense than the air around it. This would be true. Right? The warm air is less dense, but it's going up, and it's going to become more dense because it's going to cool down as it goes up. Cool air pushes warm air upward. This is not really... yes, this would be true, because if it is cooler, it would be more dense, so it would push it up. Air that is more dense than the air around it will sink. This is true. Things that are more dense will sink in comparison to things that are less dense. This is why things sink and float in water. If it's more dense than water, it sinks. If it's less dense than water, it floats. So this talks about modern houses have systems to control internal air temperatures in times of hot or cold weather. In these homes, hot or cool air is pumped into the interior of the house. Based on what you know about how cool and warm air circulate in the atmosphere, what might an engineer need to consider when designing a heating and cooling system for the home in a cooler climate? So one thing is, you may have been in a house where you see, I have, so where I live, or maybe where you live right now, we have maybe our houses, right? You have your houses, right? Here's our building. And a lot of us will have maybe vents in the ceiling or along the wall. I think it's pretty common to have vents, like those little vents for air conditioners or central heating and air, everything in the ceiling. Now, one of the problems with this is that this works really good in the if it's hot outside, because right, what happens to cold air? Cold air is going to sink, right, and warm air is going to rise. And so if you were trying to make a house and it was going to be in a warm climate, you're probably going to have the air conditioning on a lot. So it makes sense to put the air vents at the top because it's always going to be pumping out cold air, right? And then the cold air is going to sink down to the bottom of the room where people are. That works great. It doesn't work so great if it's putting out hot air, because if it's pumping out hot air, where's the hot air going? It's just staying up at the top of the room, and we're not floating on the ceilings, so that's not super helpful. So you may have been to a house at some point in time where you see that they have the vents on the floor. It's more common. I know that like whenever I've gone and stayed at like a cabin or something in Tahoe, a lot of times the vents are along the floor because it's more common that they want to warm those houses instead of cool them. And the reason that's beneficial is because it pumps the hot air out, and eventually the hot air does rise, but because the hot air is coming out along the ground, it kind of warms the house more evenly because it starts off on the bottom and then it has to rise up. So that is probably how I would design it. Works a little bit better. Here is a diagram of a convection cell, and this kind of just describes convection more. And this question says, how does the density of air affect its movement in a convection cell? And this is essentially the same thing we've been talking about, right? Is that as I guess I could type it. So the hot air is less dense, so it rises, right? You can see that here. The red is hot. You can even see here, these red ones are more spread out than these blue ones, right? It's less dense, so it rises. The cooler air then falls because it's more dense. So you have this phenomenon where it's we have these convection cells where the hot air is rising, and as it rises, it gets cooler because it falls away from the source of the heat, right? So it cools off and loses energy, and then it gets a bit more dense, so it falls, and then it gets to the bottom and it doesn't have very much energy, but now it's back at whatever the heat source is, and so it heats back up again, and you get these kind of like circling things. So together as a group, you're scared of that. Use the word bank to complete this paragraph and explain why the wind is blowing in the photo. Okay, so when the sun shines on this area, the land warms something, then the ocean. It's going to warm faster. You can tell it warms faster if you've ever been to the beach. If you've ever been to the beach during the summer, and you walk onto the sand, and the sand is like burning hot. It feels like it's melting the skin of the bottom of your feet off. But then you go into the ocean, and the ocean is the same temperature, or it's like the same temperature it usually is. It's cold. So the ocean water didn't change that much, but the sand sure did. The air above the land becomes... so that means that the air above the land is going to become warmer than the air above the water, right? Because the land has kind of become a heat source. So it's the land above the land is warmer, right? Just compare the air temperature over the water to the air temperature over the land. Well, the air over the land is going to be hotter because the land is hotter than the ocean, okay? Then the wind is blowing towards the land. You can see that with the trees. The branches are pointing in this direction. It's like the wind is going. Oops. It's like the wind's going that way, right? because the air generally moves from the cooler, high pressure areas to the warmer, low pressure areas, right? So the air over the water is cooler, so it's more dense, right? It's like all these molecules are like really tightly packed. And over the land, they are, less tightly packed. It's less dense, so the air is going to move in that direction. Exploration 2. Patterns of air circulation. So this is talking about how air kind of circulates around the Earth. And this is a hard experiment to see. Normally, we kind of try and do this in class. But what they do in this little experiment that they're showing in this picture is they have little droppers of ink and they have balloons. And you can see how in this one, the line is straight. The ink just goes straight down the balloon. And in this one, it curved. So what was that? So in this picture, this girl drops the ink onto the balloon as she just holds the balloon still. And so the ink just goes straight down the balloon. You can imagine that happening, I'm sure. Now, if you take a balloon though and you spin it, so let's say you like wind it up, where you hold it, and then you kind of let it spin around, and then you drop the ink on, you can see how this ink kind of curved in this direction while the balloon was spinning, and then eventually it looks like it stopped spinning. And so this is a phenomenon that you can see just doing this little experiment, but this is related to Earth's rotation and how wind moves on Earth. So here we have a few different examples. Now remember that the Earth spins in this direction. Okay, so the Earth is spinning around like this, right, in that direction. So this is an example of what wind patterns would look like if the Earth did not rotate. So if the Earth didn't rotate, right, what you would get is you have the sun blasting the equator more than the poles. And so what it does is it heats up the air around the equator. You can see that it's showing that right here. It heats up the air around the equator, it rises, and then as it gets into the upper atmosphere, it kind of cools, and you'd have these giant convection cell pockets kind of going all the way from the hottest part of the atmosphere, which is, near the equator on the land, up into the upper atmosphere over the poles. That's where it would be the coldest. So you have these giant pocket cells. Well, because the Earth is rotating, we have this effect called the Coriolis effect. You can see the Coriolis effect. This is why, sometimes people talk about how if you go to the southern hemisphere, right? This is the northern hemisphere and the southern hemisphere. If you go to the southern hemisphere, the water that goes down the drains spins the opposite direction. In the northern hemisphere, water goes down the drain clockwise, and in the southern hemisphere, it goes down counterclockwise. And this is literally because just like you spinning a balloon will force these liquids or the gases to kind of curve off in a certain direction, that same thing happens because the Earth is spinning. And, the Earth doesn't seem to be spinning that fast to us because we're sitting on it, but it's actually spinning around pretty quick if you consider how large Earth is and that it spins around once per day. So what that does is that breaks up these convection cells. Instead of having just two giant things, right, what you get is you get this breakup, because what happens is essentially, and this looks really complicated, but all you really kind of need to remember is that because the Earth is rotating in this direction, right, it forces around the equator, where the Earth is rotating the fastest in comparison to everywhere else along the surface, it causes the air and the water to kind of peel off and want to go this way. Okay, you can see this real easily with this. This is pretty complicated, but you can kind of see this with liquids. If you just went to your kitchen, right, or you just have a cup, right? Imagine you have imagine you just have a mug of coffee or something, right? You have a mug and it's filled with a hot coffee, right? This is the worst looking mug of all time. Anyway, if you have this mug right here, and all of a sudden someone hits the mug and the mug moves this way really quickly, what happens to the liquid? Does the liquid all fly out in the same direction? No, it would be flopping out that way, right? You can see that too, if you're ever baking. I used to do this in class, right? You hold a pan, right? Get like a baking pan, like those like baking pans that you'd put stuff in, and you can fill it with water, right? And if you push the pan this way and you just leave it on your counter so the water's moving, and if you push it in one direction, you'll notice that all the water, right? The water would be like bunch up like this. It kind of all sloshes in the opposite direction. That's kind of what's happening here, but it's happening with the air, and so it creates these broken up pockets of convection cells, because you still have different areas, right, where it's warming. It just breaks it up, and that's what gives us what we describe as the wind belts. So it's very interesting. Look at that. These are some names that people have given these different winds. The easterlies are a little less common, but a lot of people hear of the trade winds because they tend to be pretty stronger, and more people live around here anyway, so we hear trade winds. And this talks about the different names that we've given these different types of winds. In what directions do the prevailing winds blow in the Sahara Desert, the Southern Atlantic Ocean, and the Amazon River? Record your evidence. So I'll do the Sahara Desert, and you can do the rest. So in the Sahara Desert, where's the Sahara Desert? The Sahara Desert's over here. So which direction is the prevailing winds going? The prevailing winds would be these these white arrows is the direction of the prevailing winds. So it's important to know that these global winds are known as prevailing winds. Obviously, you could be here and the wind can blow in this direction. But it's most of the time it means that the wind is blowing in one direction. And so it is moving this way if you're in the Sahara Desert. So it's kind of moving southwest. So that would be southwest. Right? And then you can look at the map to figure out the rest. Okay, and here we have some things about the hemispheres. So fill in the blank to complete each statement correctly. Remember that equidistant means same distance. We're filling this in with... Oh, here we go. Okay. Because it's equidistant. So 45 degrees north and something south are equidistant from the equator. So same distance from the equator. What's the same? So 45 degrees north, you look at this here. 45 degrees north is up here, right? It would be between 30 and 60. So it would be like right here, across this way, going across like that. And so that would be 45 degrees south, are both the same distance away from the equator. So this is 45 degrees south. Something north and 78 degrees south are equidistant from the equator. Oh, so this is the same thing. So 78 degrees north and 78 degrees south, or the same distance from the equator. 90 degrees north, and this would be 90 degrees south. Right, 90 north and 90 south are the same distance from the equator. And 15 north and 15 south. So the main point of this is that we measure things going up and down on Earth from the equator, right? From the equator, which is in the center. So if you're saying 30 degrees north, it means you're up 30 degrees from the equator. If you say 30 degrees down or south, it's 30 degrees down from the equator. But both 30 degrees would be the same distance away from the equator. The city of Boulder, Colorado in the United States is about 40 degrees north of the equator, and the city of San Carlos in Argentina is about 40 degrees south of the equator. Which statement is generally true about the wind patterns of these two cities? They should blow in, well, let's look. We've got 40 degrees north and 40 degrees south, instead of just answering that. So 40 degrees north would be up here. This is kind of a busy one. Maybe let's go up higher. Erase these. So you can go back to an easier picture. Where is 40 degrees north? That would be like up here in this range. And then we got 40 degrees south. Be like around here-ish. So north, the air is moving in this direction. It's going northeast. In the 40 degrees south, it's moving southeast. So they're both going to the east, but in the north it's going to the north, and the south is going to the south. Let's check this out. What were our options? They don't blow in opposite directions, right? That means that one would be going this way and one would be going this way, but they're not. They're going this way and this way. Right? So they're both blowing from east to west. That's not true. They're both blowing from west to east, right? They're going up and down, but they're still going from west to east. So there we go. Exploration 3, relating air circulation to the Earth system. So 16 says, the Witch Fire occurred when dry, high-speed winds were blowing through the San Diego County. These winds, called the Santa Ana winds, can affect Southern California in the fall and winter. The winds are warm and sometimes even described as hot. Why might Santa Ana winds be related to high wildfire risk? Well, so this is talking about how kind of the air circulating around the Earth affects different areas. This is what this exploration is about. So this is in the fall and in the winter. And one of the things that happens in the fall and winter also is storms. So I'm not going to type this. But so you have storms and you have really dry winds. It's after the summer, right? Because it's starting in the fall and the winter. But the reason that there's a high fire risk is because it's after the summer, right? So it's very dry already. And in the fall and getting into the winter, maybe it still hasn't rained very much yet, right? And so it's still really dry. And then you have these dry, hot winds coming through. If there's a lightning storm, or, if people are camping and they accidentally let their fire get out of control or something, you've got these kind of perfect situation for fire, but then it's also super windy. If you've ever been to like Southern California and felt the Santa Ana winds, they're really powerful winds as well. So it stokes fires. So the cycling of matter in the atmosphere. This kind of goes back to that picture of how the sand from the Sahara Desert can actually blow over into a whole nother continent over the ocean. Like this is a giant cloud, and it's just sand and dust. So you can kind of brainstorm these things yourself, but some examples are, what factors might determine how far something is carried by wind, strong versus powerful winds. It could also depend on, what the wind is carrying. Ash, and this describes lightweight matter such as ash and feathers. Ash and feathers is super light, right? That's you're not going to necessarily be blowing rocks across that places, but ash can travel very far. And this talks about sediment, dust, and ash. So volcanoes have ash, and that's very fine, light particulate, and it can carry easily in the wind. Water vapor enters the air and gets traveled around. Organic matter, such as pollen, right? In the fall, you get that like green pollen stuff all over cars and things outside. Spreads around. Seeds, like dandelion seeds. Those are those seeds that have like the little, the little fluffy things, and people blow them, and they blow off into those little like sticks with those thingies. Those are seeds, and they're shaped like that so they can blow around in the wind. And there's also other things like carbon and nitrogen and phosphorus. These are other gases that are in the air that get moved around. So how might the cycling of Earth's atmosphere relate to dust traveling from the Sahara and the Amazon? Well, they can blow all of the dust from the Sahara over to the Amazon. And this sand, sand isn't just rock, sand and dirt and thing. It has all sorts of things in it. It's got carbon, it's got nitrogen, it's got phosphorus, it has pollen, it's got, maybe bacteria and stuff that's mixed in with all of that. So you have, these giant clouds of not just like rock as sand, but all these kind of nutrients blowing over, and it settles in the Amazon and helps things grow. The flow of energy in the atmosphere. So this might be a little bit familiar from the previous things. These are just examples of how energy can transfer from things in the land to the air. We've got radiation, right? Radiation from the sun coming down, and it heats up the water, it heats up the ground differently, and you have this, the warm air rises, and then it gets up in the atmosphere, and it cools down, and then it comes back down. And so we have this constant stream of energy coming from the sun, heating up the land, and then cycling of that energy up in the atmosphere. This question says, how might the transfer of thermal energy and kinetic energy by wind affect water molecules on Earth's surface and the atmosphere? How might the transfer of thermal energy, so remember this is heat energy, and kinetic energy, that's the movement of molecules, by wind, affect water molecules on Earth's surface and in the atmosphere? So on Earth's surface, right, the transfer of thermal energy, the heat and the movement of other molecules would warm water, and it could also move it around, like the waves from wind and things like that. But it can also, in the air, it says also in the atmosphere. Well, how can it affect things in the atmosphere? Well, this is why you don't see very many clouds during the summer. It's because you have more energy, heat energy, right? And it's warming the water molecules in the air, and it keeps them spread out. Whereas in the winter, there's a little bit less energy, it's colder, and so the water molecules in the air can condense more and make clouds. So those are some examples. And here is how the Santa Ana winds work and why they're hot. And this is a picture showing that. And so what we have here is we have high pressure area over here, and this is in this area that's inland, and it's hot. This is desert. So what happens is you get these low pressure areas, or high pressure areas here because the air is actually cooling at this time of the year over in here. Sorry, it's not hot. I'm mixing up because I'm staring at the pictures. This is inland, and so the weather extremes are greater, and so it starts cooling down. It creates high pressure areas, and then over here, outside the coast, it's a warmer, low pressure area, and so you get these winds that are moving across like this. As they're moving across, they are warming up because this is like out here. This is desert, and it's coming to more warm area. And so it warms up. And so by the time you're here, Los Angeles, San Diego, that's like right here. So by the time all this cold air spends all this time blowing across the desert to the hotter air, it's picked up all this heat energy. And so it's warm air and it's moving quite quickly. And so you end up with, by the time you're here, you get warm, hot winds. The atmosphere is interacting with the geosphere. Remember, geosphere is land and hydrosphere is water, so it's not really interacting with water over here. These winds can cause fires to speed and burn vegetation in the biosphere. Remember, it's burning vegetation, vegetation is living things, not land. So land is like, geosphere is like the rocks, the dirt, the inorganic, the dead stuff. Biosphere is everything that's living. So vegetation would be biosphere. Think about the witch fire in San Diego County. Explain how the Santa Ana winds can worsen the effects of wildfires like the witch fire. Use evidence from the diagram and text. I'll give you one example of how they can make it. So if you have a fire, you're in San Diego. You have a fire. You have a bunch of winds. Why is that not helpful? The winds are going to help the fire spread. Here you go. And that is it for, this is the extra stuff, but that is it for lesson 1.